Thank you very much, and thank you everybody for joining us today. It's certainly a pleasure to be back under this form. Uh, this was a presentation that I came up with and developed based on a conversation I had when I was at a NETA power test conference, not last year, but the year before. And I had a gentleman come up to me, and he worked for a NETA testing company, and he was deployed in the middle of the night to a nuclear site where he had commissioned some relays and had a relay operate on the differential. And of course, when you have such an instance occur at a nuclear facility and it's a critical GSU, that is certainly going to raise a red flag with a lot of different people. So he got on site, and by the time he got on site, the maintenance team was already there putting up scaffolding, disconnecting the transformer, and getting to run a battery of tests on the transformer to see what possibly could have gone wrong. Well, the relay engineer that approached the foreman on the job said, "Well, wait a minute, we haven't even looked at the oscillograph or sequence of events from the relay to try and make a determination." And they kind of brushed him off and said, "Yeah, we understand. Go away. We got a lot of work to do here." As it turns out, in interrogating the oscillography, that there was actually no differential current that was suspected, and it was a nuisance trip from one of the protective relays. And these things do happen. So what I've come to know in the industry, and I started out in the industry with a discipline in protective relaying, transformers included, and kind of meandered into transformer diagnostic testing just based on the company that I worked for and the focus of the equipment that they were manufacturing. So what I thought I would do is try and bring together these two disciplines to take a more holistic approach to transformer failures, because it just seems that the industry, you get some people that are field technicians that kind of get siloed, and engineers as well. You're either the protection guy or you're the transformer maintenance guy, and not everybody understands the disciplines associated with both those areas. So I kind of wanted to talk about both. And I think it's important to understand when you talk to, protection engineers and test technicians about protective relaying, you're thinking, well, my transformer is well protected. I've got a very modern multifunction protective relay protecting the transformer, as well as the Buchholz relays and rapid pressurized relays that you'll see in the slide over here. And then what I think is important to understand, and we have to realize, is that there are some protective elements for a transformer that are both proactive and reactive. Now, what do I mean by that? Well, consider a differential relay. Okay, a differential relay is looking at the current coming in and the current going out, and based on Kirchhoff's law, that should be equal. All things being considered. If it's not, that means there's a fault internal to the transformer, and you create enough differential current between the two windings to trip the relay and to take the transformer offline. Well, is that really protecting the transformer from a failure? No, it's not. Unfortunately, the failure is already there. It can certainly avoid catastrophic failure in terms of an explosion or further damage to peripheral equipment, but it doesn't mean that it's protecting the transformer from failure. Now, there are other protective relays, okay, like volts per hertz, over and under frequency, under voltage, things like that will protect the transformer from excessive damage, things like excessive heat or reverse power conditions or over voltage conditions, things that will happen externally to the transformer that could cause damage. And that's why these relays are put in place along with the differential. So I think that's important to keep in mind as we go through this. Now, basically, when we talk about transformer failures, there's three particular categories. You have mechanical, you have electrical, and you have insulation failures. And let's talk first about mechanical failures, because these involve physical displacement or damage of parts within the transformer that can happen for a number of different reasons. And of course, we think a mechanical failure, well, that's, we're moving one transformer from one location to another, or it's coming from the factory and it's going on a rail car. And rail cars have a tendency to bump and cause a lot of vibration when they're coupling and decoupling. And for this reason, we put vibration monitors on them that are sensitive if this should happen. But it's not limited to just transportation. Seismic activity, can cause physical damage. Improper synchronizing of a generator, a GSU, would take and absorb a lot of mechanical force if we were synchronizing that generator, attempting to, 90 degrees out, which would cause excessive damage. But the one thing we want to talk about today is through faults. Okay, so transformer through faults, your power system faults, these are faults that are external to the transformer zone and can cause high levels of current flowing through the transformer. And these forces within the transformer can eventually weaken the winding integrity. And a comprehensive transformer protection scheme should include protection against thermal overload, transformer overload through fault and overexcitation, as well as protection from external faults, internal faults. Okay, so the protection is there. But, one of the things that you have to consider is that when you have a fault external to the transformer, that's not something necessarily that the protective relay system is going to see in terms of taking the transformer out of service. So to kind of understand the difference between a through fault, and an internal fault, think about where your current transformers are located. You have current transformer on the primary side, and then you have it on the secondary side, and we're looking for that current differential to exceed its minimum pickup. And any fault internal to the transformer between the two CTs, that's where your current's going to flow, creating a differential current. But with a through fault, let's say this occurs on the line after the transformer, then the fault current will start flowing into the system, and this current will flow through both the CTs, okay? And this is considered a through fault. So remember, differential protection will only sense faults occurring inside the range of the CTs. And that's why we call it a through fault. It's a faulted condition external to the transformer flowing through the transformer itself. So power transformers throughout the power system will experience different levels of through fault current in terms of both magnitude, duration, and frequency. And those three things are very important in determining whether we possibly had some mechanical failure. So the recording capability of your transformer protective relays actually will allow for monitoring and recording through fault current and through fault activity. Now, in having this discussion with some protection engineers, and I was actually talking to one gentleman that's been around Schweitzer Engineering Labs for many, many years. And he mentioned to me, he said, Drew, he says, yes, our transformer differentials do have through fault monitor, as do most other modern transformer differential relays. However, in my experience, people don't want to set them, or there has been a neglect in setting up the through fault monitor in the industry. And he agreed with me that this is an important step in terms of your protective relay. And one of the things that's important to understand is that the potential damage from a through fault really depends somewhat on core design, and the path through which the flux flows makes the zero sequence impedance of the shell type transformer higher than that of a core form configuration. So through faults are typically more damaging to core form rather than the shell form due to the multi-current channels that we see in a core type construction. Now, that doesn't mean, okay, word of caution, that this type of core design can't be subjected to damage from a through fault. It's just it takes a higher amount of through fault and a higher duration than it would on a core configuration. So if we look at the logic of a protective relay for through faults, basically we're looking at a cumulative I squared T value for each of the phases and compares it against a threshold setting that would create an alarm. Now, typically, your through fault monitor is not going to take the transformer out of service. Depending on again, the three values: the magnitude of the fault, the duration of the fault, and the reoccurrence of the fault. Okay, it will typically, once you set a threshold, will send off an alarm so you can investigate. But over time, let's say you have a distribution transformer and a distribution sub, and you're seeing a fairly high number of through faults. Well, that maybe not to the magnitude where it would damage the transformer, but it may indicate that we've got a problem out there on that feeder, maybe possibly requiring some tree trimming. Okay, so there is good information to get from your through fault monitor. But excessive through fault occurrences within a given period can also indicate the need for maintenance, such as tree trimming and right-of-way clearance. So what we see here, this actual, and I apologize for being a little bit fuzzy here, but this is a report from a Schweitzer relay that has recorded some through faults in the particular system that it's on, and you'll see it does it by phase, okay, in terms of magnitude, in terms of duration, okay, and then in terms of reoccurrences. So this will, give the operator, if you do get an alarm, a good indication of when the through fault happened, what the magnitude was, and what that duration was. Now, how do we know when that's damaging? Well, how do we set a through fault monitor? Well, first of all, we have to determine what type of category the transformer falls in. And category 1 through 4 basically has to do with the kVA rating, both single and three phase. So it would be set a little bit different based on the type of transformer and what category it is. But again, it's important to know that through faults will produce physical forces that cause insulation compression, insulation wear, and friction-induced displacement in the windings. These effects can be cumulative and should be considered over the life of the transformer. Now, what does that mean for your protective reeling? Well, what that means is that if I have a digital relay that I'm replacing, or I'm bringing in a new protective relay, then the information from the old relay should be brought into the new relay, because this is cumulative over time. We want to see how many through faults that transformer has been subjected to. Okay, now there are some calculations out there that will help you determine what the through fault withstand capabilities are and how to set the alarm. So basically, we're looking at the maximum current in per unit of the transformer's base rating, and that's calculated based on the transformer short circuit impedance for categories 1 and 2. So maximum current calculations for 3 and 4 transformers are based on the overall impedance of the transformer's short circuit impedance and the system impedance, which is all available on the transformer nameplate rating. If not, it's important to get advice from your transformer manufacturer in terms of what that withstand capability are. So if we look at here at the different categories, okay, of transformers, you'll see here that it involves the time or the length of the through fault and the times base current rating of the transformer in terms of the magnitude, okay, of the through fault. And you can see they're slightly different based on the category. And then in some cases, you have to coordinate that with your overcurrent settings on a distribution relay. The most important thing, though, is to, when you go to set your through fault monitor, check with your OEM in terms of, what the capability, the withstand capabilities are for that particular transformer. Now, if we've had if we've recognized that we've had a through fault on transformers, or the alarm's gone off, or you've noticed during your periodic routine testing that, hey, we've had a number of through faults, maybe it's important for us to look and check on our diagnostic testing to see if we've had any mechanical failures. And the two different types of tests that we run to determine mechanical failure on larger oil-filled transformers are going to be your sweep frequency response analysis, your SFRA, and then also your leakage reactance, both three-phase equivalent and per phase. And again, if you need a guidance on these particular types of tests, IEEE C57149, which is a guide for application and interpretation of frequency response analysis for oil-filled transformers. This is currently in revision right now, and hopefully by the next Transformers Committee meeting, which will be this fall, we will have approval and get this thing published. But all it did was extend some of the information available for this type of test. And then C57152, the guide for diagnostic field testing of transformers, regulators, and reactors is also available to talk more about the leakage reactance tests. Okay, so an SFRA test is there to evaluate the mechanical integrity of the core, the windings, and clamping structures within the power transformers. Now, what can be the result of a high through fault? Well, you can have core movements, faulty core grounds, winding deformation, winding displacements, partial winding collapse, hoop buckling, and you'll see this indicated in some of the illustrations here. These are transformers, again, that have been damaged, that are showing mechanical failure in the windings. Now, basically, transformers generate a signature. Now, this is the whole purpose of SFRA. And one of the important things is that we have to have a baseline of the frequency response. Okay, and it's important that if you're ordering a new transformer, you're specifying a new transformer with the OEM, make sure before it leaves the factory that you get a fingerprint of that SFRA and that test is performed and that record is available for you, because you'll want to check it again and run the exact same test once it gets ready for commissioning. But it is an offline test, a very low voltage. It's not intrusive, typically less than 10 volts. And then the changes can be detected and plotted as a response curve when test signals at different frequencies are applied over the windings. So changes in frequency response can be compared over time between test objects or within the test objects. In other words, we can compare an original trace to a new trace, but we can also compare traces between windings and between phases. But it's important, think of it as a fingerprint. Each transformer has its own fingerprint in terms of what that trace would look like when you first test it. The test procedures are fairly simple, as we see here. You have an output of your voltage. Okay, you have a reference channel to make sure that what you're putting in is exactly what you're using comparatively in your measurement. Okay, and then you have your measurement channel. And this is a typical configuration on a 2-winding delta-Y transformer. Now, one of the things that's important to note is, like, it's not just one single test. We are comparing, as you'll see here, it's kind of like a chest x-ray. When you go for a chest x-ray, they look from front to back, then they look back to front. Then you turn to the side and they look from one side to the other, and then from the other side to the other. And that's kind of what we're doing with the SFRA test. And you'll notice here, and again, this is part of the recommended test from C57149, and this is for a delta Y transformer. And of course, this has a 30-degree phase shift between windings. So you have a high voltage, okay, reference H1 to H3, and that's an open circuit test, H2 to H1, H3 to H2, etc. And then your low voltage, X1 to XO, X2 to XO, and this is, again, an open circuit test. So we've got 6 open circuit tests between the primary and the secondary windings, and then we have a short circuit test, okay, on the high side, and then the low side, which you're shorting. Okay, so it's important to go through, whenever you're doing these types of tests, go through the manual carefully, refer to the guide. Now, in terms of your response that you're getting from your SFRA test, we can kind of identify what portion of the transformer we may have an indicated problem. The lower frequencies indicate problems within the core itself. And then in the middle frequencies, this is an interaction between the core windings. And then in the higher frequencies, this would indicate an issue in the winding structure itself. So this is kind of pinpoints exactly where in the transformer we may have a problem. Now, here's an interesting analysis, because remember, a number of things can cause physical displacement in the windings. It could be from, seismic activity or moving the transformer from one location to another. But what we see is that winding movement that's typically caused by a high current through fault in a three-phase core form transformer is generally associated with the low voltage winding in the form of radial deformation. So your diagnostic focus will be given to the low voltage open circuit and high voltage to low voltage short circuit responses. And again, this is you can find all this information in C57-149. Okay, so open circuit and high voltage to low voltage short circuit responses are really where you're going to see an indication of possible damage caused by a through fault itself. Okay, the next test we're going to do, and this is kind of important, is it's called a leakage reactance, or we also have known this as a short circuit impedance test. So the field leakage reactance test, this is an AC test at 60 hertz, and it is, again, a short circuit impedance test. And basically what we're going to do is we're going to measure the impedance of the transformer on all three phases. And we're going to do this under two scenarios. One is called a three-phase equivalent, because we can only do this a single phase at a time. But when we do the three-phase equivalent, we'll marry all those results together and then compare that with the nameplate data, the impedance measurement stamped on the nameplate. Well, think of this. Think of that we have a wooden trough, and in that wooden trough is water flowing down the trough. Well, normally as the water flows through, it's going to have some normal resistance. It's an old wooden trough, and you may have some leakage that spills over or whatever, and this is normal. Well, consider this: if you have physical damage to that trough, or somebody takes a rock and throws it in the middle, you're going to get you're going to get a higher resistance. Okay, you're going to have more leakage. Well, leakage flux is kind of like the same thing, and that's what we're looking at. So it is normal that some flux escapes. And this leakage flux also helps create an impedance that is used to limit short circuit current. Leakage flux creates a reactive magnetic energy that behaves like an inductor in series in the primary and secondary circuits. So that impedance can be easily measured, analyzed, and trended. Okay, and we can see here that we have a simple model of your RL circuit on how flux is cut through the transformer, the primary and the secondary winding. And then here's your main flux, and then here would be your leakage flux between the windings. And this is, of course, normal. So, one of the very, very important things, not only as a protective relay guy or field technician for relaying, but also for people doing diagnostic testing on a transformer, it's very important to be as familiar as you possibly can with the nameplate rating of the transformer. I mean, this is basically how you set your protective relay elements. Based on this information. This is also how you compare diagnostic test results for certain tests. And one of those is leakage reactance, because before the transformer leaves the factory, they're going to measure that impedance in percent and stamp it right onto the nameplate. And that's what we see here in this illustration. Now, basically what we're going to do is we're going to do two types of tests: the three-phase equivalent test and the per phase test. And you'll notice that we're doing a three-phase equivalent. Okay, we have shorted out, okay, because it's a short circuit impedance test. We're going to measure the impedance between H1, H3, H2, H1, and H3 and H2. Okay, so this will give us an equivalent three-phase impedance circuit measurement. And then we're going to do it per phase, okay, H1 to H3, H2 to H1, and then short the X bushings accordingly here to our connection diagram. Okay, so a three-phase equivalent, basically what we're looking at, you can see the formula here. I won't go into it in too much detail because I don't like math. But anyway, you can see here that based on the measurement here, we get a measurement of 6.73, and basically your three-phase equivalent should be within plus or minus 3% of the nameplate rating of the transformer. Okay, 3%, that's our maximum allowable tolerance in the measured three-phase equivalent as opposed to the nameplate rating. Okay, now the purpose of the three-phase equivalent is to produce test results to compare to the factory short circuit impedance. Okay, if one or more of the per phase measurements is dissimilar from the others, then a mechanical failure may exist within the transformer. So what typical tests do we see on oil-filled transformers? Well, we see a lot of different types: power factor, excitation, TTR, winding resistance. Okay, in the middle there somewhere, usually after your excitation test, should be leakage reactance. Okay, it's a simple test to perform, but why would I do a leakage reactance test? Well, a couple of reasons. Number one is that you suspect the transformer may have be subjected to through faults between the last testing cycle. Okay, you may not have a through fault monitor in your protective relaying system active. So this would be your first line of interrogation to see if those through faults have caused, or if your through fault alarm, has given an indication that you've had excessive through faults or one high through fault, or so on and so forth. So leakage reactance can be your preemptive test to the SFRA, because if leakage reactance comes out okay and all your subsequent tests come out okay, then SFRA in all likelihood will not be necessary. Okay, so let's take a case study here. All right, this is a 50 MVA transformer configured as a DY1, and the differential relay tripped from service, and oil appeared to be leaking from the low voltage de-energized tap changer. Okay, and that's a tap changer that's embedded into the tank of the transformer. Your standard test protocol was applied, which included SFRA and leakage reactance. So unfortunately, in this case, the power factor test wouldn't even run at 10 kV. So they lowered the voltage, of course, and they pushed through, and the power factor was almost 50%. Now that is totally indicative of a problem or a failure. Now, subsequently, we looked at the DGA results, and what you'll notice in the DGA results here over time, and we started back in 1994, your acetylene went from 0 all the way up to 21. And that is definitely indicated that we've got a problem in the transformer itself. And remember, transformer diagnostics doesn't come down to just one particular test. We want a whole series of tests to get as much information as we can as to what may have happened that caused this differential relay to trip. So here's an interesting slide right here. And what this shows is that when we ran our leakage reactance test and we did our three-phase equivalent, you'll see that the difference in the impedance was only 2.65%. And that's well within the 3%. But when we did the per phase measurement, you'll see right here that the B phase was way out of whack, much higher than 3% of the other two phases. And that's what we're comparing each phase to each other. And that should be within 3%. And this was 9.62. Obviously, we got a problem on B phase. Now, if we look at our SFRA results, this indicates a high impedance fault on phase B on the low voltage winding. And remember what we said about where through faults give you an indication on your SFRA. It's in that low voltage winding. So both the low voltage open circuit and high voltage to low voltage short circuit tests provide this evidence. Okay, so this clearly illustrates a failure mode on phase B. And this is what we saw when we detanked the transformer and tore it all apart. Serious mechanical failure resulting from a through fault. Okay, let's switch gears here just real quickly and talk a little bit about insulation failures. So one of the biggest concerns that surround life extension of power transformers is the health of the insulating materials, and not just the oil, but the polymers and the paper and the windings themselves. And we know three things will cause accelerated aging, and those three things are moisture, heat, and oxygen within the insulation itself. That's a significant impact on the life expectancy. Now, when we talk about insulation failures, The insulation in most of your power transformers consists of both oil and cellulose, which of course is paper and pressboard. The solid insulation is divided into major and minor insulation structures. Your major insulation systems includes barriers, spacers, and clamps, while your minor insulation consists of the winding insulation, the paper, and the polymers. Cellulose type transformer insulation, it actually serves three different functions. It acts as a dielectric by storing electrical charge when the transformer is energized, and isolates transformer components that exist at different voltages. It also fulfills a mechanical function by supporting your windings and contributing to improved thermal health of the transformer by creating cooling ducts for the oil. Okay, the oil has to provide sufficient dielectric strength, and that provides sufficient cooling. It'll preserve the core and oil assembly by filling voids in the insulating materials and minimize contact of oxygen with the cellulose and other materials that might be at risk of oxidation. You can see here, I mean, it's similar to what you have in your automobile. Okay, the lubricating properties of oil start to degrade over time, and it becomes dingy and dark and full of sludge, while it should look like this nice clear sample over here. Okay, so if we're concerned about moisture, we have to understand where moisture comes from. A number of years ago, I was out in Colorado at a local utility, and we were talking about moisture in transformers. And one of the comments from the engineers was, well, we're at a high elevation here. We have very little relative humidity in the air. And I said, well, that's understandable, okay, because whenever you have a leaky bushing, or you're doing maintenance on a bushing, or you're exposing the tank to any kind of outside atmosphere, you always have the opportunity to have moisture ingress. But moisture can be present during the manufacturing or final assembly process. You have leaky gaskets around your bushings or your radiator, or even the transformer design, such as a free breathing conservator with a bad desiccant, can absorb moisture right into the conservator tank if you don't have a nitrogen blanket. But I think the most important thing to understand is that moisture accumulates from the natural aging of the insulation. And how does this happen? Well, degeneration of the cellulose material within the transformer ultimately is going to determine its in-service life. We measure the strength of the cellulose in the paper in terms of what we call degree of polymerization, or DP. And the strength of that insulation is measured, and a brand new transformer should have a DP rating of about 1800. But as the cellulose starts to age, it breaks down into smaller chains or links, and the DP values start to degrade. And if you get a DP value of anywhere from 200 to 300, basically your transformer has reached the end of its life. But as these molecular bonds in the cellulose and the resin start to break down, the byproduct is moisture. So as the insulation starts to deteriorate over time, which again is caused by heat, oxygen, and moisture, of course, so it's self-perpetuating. So what happens is we have no exposure at all to the air, okay, but we also can get a large ingress of moisture. Now, if we look at what we call the Lungard chart, this is a Lungard chart developed by Lungard and a couple of his brainiacs. This shows you two things: that insulation life expectancy right here, okay, in terms of years, is relative to the heat, okay, and the moisture content in terms of percentage. So overheating can result in can be the result of poor cooling systems or operating conditions such as excessive volts per hertz or overloading. Okay, and we'll take a look at that in terms of how protective relays deal with that issue. But excessive moisture in combination with high operating temperatures can greatly reduce the life expectancy of the transformer. Well, why is moisture bad? Well, moisture basically lowers the bubbling point in the transformer. And this will create voids in the insulation and eventually lead to partial discharge. And the PD, again, can lead to excessive deterioration of the insulating paper, and the damage to the insulation is irreversible. And this is important to know. It's important to get a good assessment in terms of your moisture content in the insulation so that you can take corrective action before it gets worse. So it's kind of a chain effect. So the moisture embeds in the voids of the paper, causing the discharges. That leads to carbonization, and that can lead to a treeing condition, and that can cause a severe breakdown in the insulation, as we see in this illustration right here. Okay, and here's just a look at how some of that can appear in terms of, and it doesn't damage just the windings. You'll see here other components of the transformer where the insulation is severely broken down because of moisture. So what is allowable? Well, the proportion of moisture to oil versus cellulose greatly depends on operating temperature. And this is one of the problems that we have with measuring moisture during a dissolved gas analysis. Now, the laboratories do an excellent job at measuring what they have in their possession, and using equilibrium curves if you've recorded the oil temperature at the time of taking the sample. But remember this, when you take a transformer offline, the moisture moves from the oil into the insulation itself. Okay, so there's not a direct proportion of moisture in the oil versus the insulation. Okay, so what IEEE tried to do was establish what they call equilibrium curves, and that is to try and use temperature correction to try and estimate what is actually percentages in the oil versus what's in the insulation. And it's the moisture in the insulation that, of course, we have the major concern with. So, think of this: oil samples can become contaminated from exposure to the outside air. That will influence it, and it doesn't take long for that to happen. Also, the way you take the sample has to be done very carefully. The temperature correction has to be measured very carefully. Okay, and think about this: what happens if you're going to measure the oil temperature? What happens is you draw that oil sample through the ball valve. What's it going to do? It's going to cool down, right? Okay, so there's a lot of issues with regards to that. But what IEEE tells us that depending on the type of transformer, you have a certain allowable maximum water content in ppm based on the operating temperature and what the equivalent water content in the paper should be at. Okay, so you'll see that in most extreme cases, 3% moisture content should be your maximum. Now we're talking about mineral oil. We're not talking about FR3 or any of the synthetics because they do have a much higher absorption rate. And this is something that the industry has not quite yet developed standards for. But if you talk to people from Cargill and other people that make synthetics, they will tell you that the withstand capability is much greater in terms of a ppm measurement on FR3. Okay, so how do we first determine if we could possibly have moisture? Well, the first thing we're going to do is we could do a power factor test, okay? And if we do our power factor at 60 hertz, a CHL may show a slight rise in power factor measurement if you have excessive moisture. However, it's hard to determine whether that's moisture or whether it's just natural aging of the overall insulating system, which could occur. But what we've learned is that in the industry, if you do what's called variable frequency power factor testing, you will see here that you may have elevated power factor in the low frequency range versus lower power factor. And we want to look at this angle because what this could indicate is that what you have shown here are what we call conductive losses. Now, what's a conductive loss? Well, that could be furans, it could be sludge, excessive sludge in the oil. Could be a number of things, but one of the things it could be is moisture. All right, so if we have two like transformers that we've done a 60 hertz measurement at, and they both look identical, but when we look at the lower value, the lower frequency, say from 10 to 60 hertz, if it's coming in higher or coming in lower. If it's coming in lower, that means we probably don't have any conductive losses to be concerned about. Now, if that coincides with your ppm measurement, you should be good to go. If it's higher and your ppm measurement looks higher, okay, in this range, you're showing conductive losses, then it's recommended you do what's called a dielectric frequency response. Okay, and that is, again, a non-invasive test. It's similar to SFRA, but not really. It's looking at either the power factor or the tangent delta, which is identical, similar to power factor, but looking at the other side of the angle. And what we're looking for is over a much extended, larger frequency range to see if there is excessive moisture in the insulation itself. And that's basically what it's looking at. It's looking at the percent of moisture in the insulation. Now, how was this developed? Well, it was developed, I think it first became an IEEE standard back in 1997, C57162. And it is temperature sensitive, so it's important to know what the temperature of the transformer is when you're doing the test, and it can take a while to test. But basically, how this was developed, it was developed under laboratory standards where they did a Carl Fisher titration on paper insulation, and based on the tangent delta measurement that they took, knowing what the exact moisture content was, they looked at the geometry of the response. So if you see here, what you'll see is your tangent delta measurement, and this is your frequency range here. And based on the geometry of the response of the curves, they could correlate that to the exact moisture content in the insulation. Now, through the naked eye, this may be difficult to look at this figure right here and say, well, how much moisture is that? Well, what's nice to know is that based on these algorithms, the software in these devices should be able to do this, or will be able to do this for you. So you can see at the different responses. Okay, so we have a higher geometric response right here is 3.4% moisture, and that's problematic. 2.4% as opposed to very low moisture content, 0.3, just based on the response that we get from this test. Okay, now, what happens when we do determine the fact that we have a wet transformer and the insulation needs to be drying? There's a lot of different types of methods. Okay, you can bring in a processing truck while the transformer's offline and do a hot oil spray. And, I've had some people tell me, well, I had one guy from Weidman tell me that trying to use that approach, it's like trying to raise the level of the ocean with a shot glass. May or may not be accurate, but one of the things that we found, and we rent this piece of equipment quite often, it's an online drying system, and basically it is a device that connects to the transformer while it's online, and then filters the moisture automatically out of the oil itself. Now, what's the difference? Well, the difference is that you're doing this drying process while the transformer's online at the operating temperature. And as it draws the moisture out of the oil, it's also pulling it out of the insulation. So it does take some time depending on the amount of moisture, the size of the transformer, but it's just also goes, if you have had a gassing problem and you've identified what that gassing problem is and you've corrected it, it will also degas the oil, goes through a degassing cycle as well. But it's highly effective and quite simple to use and self-monitoring, so you don't have to worry about broken lines or broken hoses, or you can actually monitor it online through a cell phone. Okay, so the next thing we have to be concerned about with the insulation system is heat. Okay, excessive heat. And where does excessive heat come from? Well, it can come from inefficient cooling systems, radiators, fans, cooling tubes, excessive loading. Okay, that's a big one, especially in distribution applications. Improper input voltages, or voltage over or under in excess of 5 to 10% can cause overheating. No load current is high and you have insulation between coils that may be damaged, unbalanced loads, improper grounding. But one of the things we want to look at is also what's called a volts per hertz condition. Okay, and this is typically referred to from PSRC, Protective Relay and Controls Subcommittee, as abnormal system conditions. Okay, and if we look at our protective elements associated with heat, okay, in transformer protection, you've got your overexcitation, a thermal overload, and then overvoltage. All three of these conditions can cause excessive heating, and then will protect the transformer from that happening if enabled properly. So what is volts per hertz protection? Well, that's the that can potentially damage the transformer from having an over voltage and under frequency simultaneously. So that's not just one or the other, but it's a combination of both and a ratio of voltage to frequency. In some terminology, it's called overexcitation. Okay, so if the difference between overexcitation and overvoltage, well, overvoltage reacts to dielectric limits. So we exceed those limits and we risk putting on essentially just punching a hole in the insulation. Overvoltages in power network can be caused by lightning strikes, overhead transmission lines, circuit breaker switching operations and faults. Anything that would subject just to an overvoltage. Well, what is overexcitation? Well, we also refer to that as overfluxing. And that's the voltage exertion that may be less than prohibited in terms of dielectric limits. So in other words, if you're just talking about voltage, the voltage excursion limit or the overvoltage condition would be A, high, but down at this level, which is still high, but your frequency is dropping, now you've got a cumulative problem that can cause excessive heating and damage to the asset. Now, this is the biggest the most transformers subjected to this condition are those that are GSUs. And that has a lot to do with failures in the automatic voltage regulation and your excitation system. Remember the other term, overexcited? So what we know is that the generator is directly connected to the GSU, and then you have your breaker, as you see right here. Well, anything that happens to the generator in terms of it coming up online or coming up to speed, that transformer is also going to be subjected to as well, because there's no breaker in between. Sometimes you do have a breaker in between, sometimes you don't, but it's important to understand that if your GSU has no breaker between the generator, whatever happens to that generator is going to happen to the transformer as well. So how do we set a volts per hertz a limit? Well, it's based on time and then percentage of volts per hertz. So most transformers, all your transformers come with a volts per hertz withstand capability, and these are thermal limits. And these thermal limits should be defined in the transformer spec. If not, there's plenty of resource material out there to find in terms of what that setting should be. But you'll notice here that you have a overexcitation plot for the generator itself, its limitations, and then the transformer limitations, and then the setting that is a bit more conservative than both, which means that if I have, let's say, volts per hertz of 120%, okay, and that's around for, less than a minute, I'm probably going to trip and take the transformer offline. Okay, so this can happen, overexcitation can happen from a number of different reasons, but we usually enable this protection on a GSU because it has to do with a faulty AVR, or voltage regulator, or excitation system. Now, it's also important to know that if you get into high voltage situations, that you can have system conditions that cause overexcitation as well. Generator load rejection, power system idling, Ferrani effect from breaker failure downstream, capacitors and reactors that should be either on or off that are in the opposite direction, or runaway load tap changer controls. So is it important in some situations to enable volts per hertz protection on a non-GSU high voltage transformer? I would say yes, it is. It certainly will do no harm. And given the fact that you could have any of these system conditions to create that is important to know. Now, if you're a protective relay guy, you'll know that a lot of times what we do is we have on a GSU what's called a fifth harmonic restraint or blocking. Because when you get into a volts per hertz condition, even if it's not high enough to create a problem, it can create differential current that the relay is going to see. So what happens is, in order to avoid a nuisance trip in just a momentary excursion or a very low volts per hertz, we block, okay, that we block the transformer differential from operating by looking at the fifth harmonic content that the relay is seeing in the current itself. Okay, and what that will do is block the relay from misoperating. But if that volts per hertz gets high enough that it exceeds the limitations and the settings, it will trip anyway. So if we can look here and we can see a unit connected generator with a high side circuit breaker was open, and it's connected to the GSU on the low side. And excitation, there was a big boost in excitation, and not exactly sure why, but it was probably caused by the static exciter, where we see a very high amount of current flowing through, and the flux is spilling over. And what we see here is that flux spills over in terms of excessive heating, especially in the non-laminated components. This is where you're going to have a problem. So if we don't trip that generator offline, we're certainly going to see a catastrophic failure. And if you look at the windings from both transformer and from the static exciter, okay, or the generator, you can see that we get severe overheating and damage that can be the result of overexcitation or a excessive volts per hertz condition. All right, so that kind of wraps it up for me. And thank you all for joining. And I'll go ahead and take any questions that the team may have.
Okay, thanks very much, Drew. Yeah, we have a few questions. How long does it take the drying process typically to take? How long does the drying process take typically?
Well, depending on which method you refer to. Now, if you're referring to the dry out system that I was referring to, the one that goes online, it greatly depends on the content of the moisture, the size of the transformer itself, and it can take anywhere from 2 to 3 weeks to a month, depending on those conditions. We typically, I've seen it take as far as 2 months. Duke Energy had a problem years ago with free breathing conservators on a number of old transformers, and they knew they had excessive moisture problems, and they bought a number of these systems for their own personal use, and then they'd rotate them between transformers and eventually get them all down below that 1% moisture level, which is a great position to be in terms of extending the life of the transformer.
Is there a relationship between transformer loading and failures?
Yes.
And diagnostics in the oil?
Absolutely. What we see when we have excessive loading is you have an overheating condition. And remember the 3 things that will destroy the insulating materials at an accelerated rate: moisture, heating, and oxygen. So a lot of people, especially in distribution applications, and even outside the fence on the substation, people put load monitors on their transformers, or are very careful to do load studies to make sure those transformers aren't overloaded. And I think in distribution and in terms of being outside the fence and in industrial and large commercial applications, this has been a problem because people aren't paying that close attention to it. They have to add another section or a couple more circuits, add more loading to the one particular circuit, and they're not careful to make sure that they're not creating an overload for that transformer. It's important to make sure that you do load studies. You get out your meters and your PEL 103s, and you make sure that you aren't overloading that circuit, because yes, that will cause early failure of a transformer.
In the last presentation, Fouad mentioned that Seagray identified 40 to 50% of transformer failures were the result of tap changer failures.
Mm-hmm.
But I asked him why that was. Is there a good answer for that?
Oh, absolutely.
Why do they fail so high? Why are there so many failures?
Absolutely. Well, first of all, you have to understand it's the only moving part in the transformer.
Right.
So you have that's why it's subjected to mechanical failure. But also what you have is you have a consistent amount of arcing and sparking. Now, if we're talking about the main transformer itself in the main tank, in your windings, if you have arcing and sparking and things going on like that, you've got a serious problem. Okay, and you're going to start seeing in that in your DGA. Well, in a LTC cabinet, you have a normal amount of gassing going on because of that arcing and sparking. Now your resistors, okay, your bridging resistors should minimize that arcing and sparking going on, but there's only so much they can do when it's making and breaking high amounts of current over a continuous amount of time. The biggest thing that I see in terms of why they can constitute the highest amount of failure is because they don't get enough attention in terms of diagnostic testing. Somebody showed me a picture of an OLTC cabinet where they had taken the door off, drained the oil, took the door off, and it was completely coated in sludge. Okay, completely coated. And this, of course, is a result of that arcing and sparking and getting moisture embedded into the cabinet itself, and just a result of neglect. So it's the one area, I mean, we all think of diagnostic testing as, well, we're going to do power factor, we're going to do TTR, we're going to do winding resistance, excitation. We'll do all these tests on the windings of the transformer and not pay close enough attention to the LTC.
What is the most serious gas to find in oil? Is it acetylene?
Yeah, most certainly. It's the one that indicates. But what you have to be aware of is that there are certain conditions that create certain gases, and they can all be bad. Okay, and it depends on the extent of the failure. Overheating, okay, arcing and sparking produce different types of gas. And if you refer to some of the IEEE reference material, you'll see what types of gases relate to what types of conditions. Severe overheating, yeah, you've got your acetylene, but there's other types of gases. For instance, we had a auxiliary transformer just delivered to a customer where it had a loose ground in the tank, and they had a high amount of hydrogen. Again, arcing and sparking. Is one worse than the other? Yeah, I could say that acetylene is probably the most combustible. Okay, but that doesn't mean that it's any worse than any high amounts of other gases as well. It just pinpoints a different area of concern.
Do people rent online DGA monitors?
I think they're probably not. We don't have any. We have a portable DGA, dissolved gas analysis kit, that you can take out into the field and get instant results on your DGA, which includes ppm. But monitoring systems are usually installed and remain installed, because that's what you're going to do. I mean, the purpose of a monitoring system that's permanently installed could help you eliminate the amount of time between periodic and diagnostic testing. But remember, a monitoring system is only there to alert you to a possible condition. It's not going to necessarily shut the transformer down or tell you, you can set limits for it. I'll give you a good example. You putting moisture sensors into the tank to measure your relative humidity, and you're measuring moisture in the oil, not in the insulation again. But what you want to do is probably use your monitoring system to establish benchmarks, and then you could see over time if it starts to elevate, and then further investigation. But it will not entirely replace the diagnostic testing, I can tell you that.
All right. Thank you for the answer.